Welcome back to Chemistry A. This is Unit 3, Quantum Mechanics, Intro to Bonding, Day 3. Now let's do a little bit of a refresher here before we get into ionic bonding. I need you right now to define what an ion is, and I need you to define what a valence electron are. So please define an ion and define a valence electron. Okay, thank you for doing that. Now, remember, we have compounds that are composed of cations and anions, and we are calling these ionic compounds. Okay? Now don't forget, a cation is a positively charged atom which has lost its electron and become a cation. Okay, and an anion is a negatively charged atom which has received an electron, so it becomes negative. Okay, so let's take a look at table salt. All right, table salt, as we know, it has one valence electron in its outer shell, as shown here. Chlorine, as shown here, has 7 electrons in its outer shell. Okay, a cation will form when the sodium atom has lost its electron. And the chlorine atom will form an anion when it gains the electron from the sodium. And this produces an ionic bond. So the sodium, which is a metal, will give to chlorine its electron, and chlorine, the nonmetal, will take the electron from sodium, and it will make an ionic bond called table salt. So Na plus Cl will produce NaCl. Okay? Ionic compounds, after they bond, will be neutrally charged even though they are made from ions, because the total positive charge of cations will equal the total negative charge of the anions. Na becomes Na positive, 1 positive, chlorine becomes Cl negative, 1 negative, 1 positive, and 1 negative balance each other out. So that makes that atom overall, after the bond, that compound, after the bond, neutrally charged. Okay? Anions and cations have opposite charges and attract one another by means of electrostatic forces. Opposites attract. These are the forces that will hold ions together in ionic compounds. For example, sodium chloride. Please at this time draw the bond on the bottom of page 194 in the box. Okay, as you can see above in the box that you have drawn, the bond that you have drawn, after Na loses its 1 valence electron and chlorine gains 1 valence electron to become stable, they will each obtain noble gas configurations. Okay, and what that is a stable octet. Na will achieve the same stability as, same electron configuration as neon, because it loses its 1 electron. And when it loses an electron, this is very important, it's not written down, you may want to write it down on your notes on the side here. When sodium loses its electron, you cannot have an empty energy level. Therefore, it disappears, leaving the second energy level to have 8 electrons in its full shell, and now it is stable. Chlorine will gain that 1 electron from sodium, and it will go from 7 valence electrons to 8 valence electrons in it, just like argon will have 8 valence electrons in it. Now remember, what I mean by these two obtaining noble gas configurations, Na is not turning into neon, and chlorine is not turning into argon. What is happening is their electron structure will look like neon for sodium's sake, and chlorine will look like argon. Okay, but it's not, they're not turning into new substances. They are still the same, they just have 1 less or 1 more electron. Okay, now we have properties of ionic compounds. Most ionic compounds will exert certain characteristics or properties, and those properties will include crystalline solids at room temperature. They will be arranged in a crystal lattice. Open your book to page 197 and take a look at that picture, and you will see what a crystal lattice looks like. Most ionic compounds will generally have high melting points. Okay, excuse the spelling error there on in the presentation. That should say points, not points. Why do these have high melting points? Because there's large attractive forces between the positives and the negatives, causing a very stable structure. And because that force is so strong between the positives and the negatives attracting to each other, it takes generally a lot of force or energy to break those bonds, and therefore higher melting points. Okay. And number 3, most will conduct an electric current when melted or dissolved in water. Why is this? Well, because when they're melted down, the crystal structure will break down, allowing those cations to migrate or move freely to one another. And in the case of where there's an opportunity, they will migrate freely to one electrode, and then the anions will migrate to the opposite electrode, and therefore energy, electric current will be transferred. Okay. The second type of bonding, one that we will not spend a tremendous amount in the chemistry, is metallic bonding. Of course, you can probably figure out we're talking about bonding that is taking place between a metal and another metal. Okay. Ionic bonds are metals to nonmetals. Metallic bonding is bonding of a metal to a metal. And this takes place with the idea of the valence electrons being modeled as a sea of electrons. Means the valence electrons are mobile and can drift around freely from one part of the metal to another. Okay, these bonds will consist of the attraction of free-floating valence electrons for the positively charged ions or cations, as you can see here in the drawing, as well as the drawing that I would like you to draw into your notes on page 201. Please draw the figure 7.12, the right half, part A and B, please. Now, the sea of electron model will explain physical properties of metals. They are good conductors of electricity. They are ductile, which means you can draw them or pull them into wires. And they are malleable, which means that you can hammer them or force them into shapes.